Welcome to the Pioneer training video for the calculation of takeoff and landing performance data in the British Aerospace 146. This video will step you through some worked examples calculating takeoff and landing performance cards based on the method developed in the Standard Operating Procedures Manual, Issue 4. So this scenario is based on example 2, but with a higher takeoff weight. As a reminder, example 2 was a departure from Bankstown off a wet runway 29 centre with an ambient temperature of 8 degrees requiring engine anti-ice on. We selected a straight out departure, and based on the engine thrust card and the rack manual, we calculated that we could use maximum flex of 26 degrees. However, now we're going to increase the TOW a little to 35,950. This in turn will increase the corrected takeoff weight and eventually preclude us from using maximum flex and take us down a different route in the procedure. So what does our diagram tell us? So looking at step 8 and 8A, if we can't achieve max flex, we're going to consider a different flap setting to see if we can optimize the performance solution. So with a higher takeoff weight, we end up with a higher corrected takeoff weight. Other than this, the example mirrors example 2 right up to step 8. So what we'll do now is just pop into step 5 and have a look at our new higher corrected takeoff weight, and then advance to step 8 where we'll ask ourselves the max flex question. Before we get down to the business in step 8, a quick update of step 5, corrected takeoff weight. So with a new higher TOW, we also have a higher CTOW. And as before, we take the TOW, add the adjustments to get the CTOW ready to compare with the most limiting RTOW from the rack manual. Right, now that we've got a new CTOW to play with, let's skip ahead to step 8. Remember that prior to step 8, we decided from the point of view of both operational, that is wind shear, low vis, and performance capability, we were going to be able to flex. Step 8, remember, checks to see if we can use max flex. So we need to hit the engine thrust table. And here we are back at step 8 with the engine thrust table. With our increased CTOW, can we use maximum flex? So firstly, here is our flexible range from 16 to 26 degrees. Remembering that this blue engine thrust table is for engine and ice on, so these temperatures are correct, but do not account for the performance required for takeoff. However, to take these temperatures into the rack manual with engine and ice on, we need to add 12 degrees to them. That makes our potential flex range 28 through to 38 degrees as far as the rack manual is concerned. As we work our way across to the right from our augmented maximum flex temperature of 38 degrees and extract the two limit weights, we rapidly come to the conclusion that the runway RTOW limit is in fact less than our corrected takeoff weight. As such, we cannot use max flex. So looking at our diagram, this is where we change from example 2, and instead we'll move into step 8A and see if a change of flap gives us a maximum flap takeoff. So given the runway constraints, it would make sense that an increase in flap might give us better performance. Based on what is shown here for flap 24, how about flap 30? Okay, so here is our Bankstown wet flap 30 runway 29 centre full length no DP chart, a straight comparison with the flap 24 chart beside it. So again, we start with our flex temperature based on the engine thrust card, but we've added 12 degrees because we're in the rack manual and we're engine anti-ice on. Therefore, we're entering the chart again at 38 degrees. And right off the bat, we can see that there is a significant drop in available performance. While the climb limit is down quite a bit, it's not limiting, but the runway limit is in fact about 1,500 kilos below the flap 24 figure. With one minor caveat, it's pretty clear that flap 30 is not the answer we need it to be, and we're not going to be using max flex today. That caveat I mentioned is the adjustments we used. Remember that our corrected takeoff weight is based on our takeoff weight and the adjustments we took from the flap 24 chart. If there's a significant difference in the adjustment values between the two different flap setting charts, this would impact our CTOW that we're going to use in the new flap setting. For our takeoff today, there is in fact a 1 kilo difference in the low QNH adjustment. While the flap 30 adjustment is lower and therefore less of a performance decrement, 1 kilogram per millibar isn't going to be much help today. Perhaps it's worth noting that the difference in tailwind decrement is more significant, with the flap 30 adjustment being less punishing to the order of 130 kilos per knot of tailwind. We're in a headwind, that doesn't help us today, but it is worth remembering that for a strong tailwind takeoff scenario, increasing flap might not give you the raw runway RTOW limit improvement you would be hoping for, but the significant decrease in tailwind adjustment might just make up for that and give you a flap 30 as an option. In any case today, flap 30 is not going to give us max flex. In fact, it's significantly worse than flap 24. So we're moving ahead with a flap 24 takeoff, but an intermediate flex thrust solution. Let's continue on with step 8A and see how that's done. So here we are with our flap 24 wet runway 29 center chart, and for the last time we're in at 38 degrees across to the runway limit that we've worked out is less than our CTOW. So now we move up the runway RTOW limit column until we find an RTOW limit weight that is higher than our CTOW of 36.4 tonnes. Now, having found a line of performance that meets our need, we need to head left and find out what that flex temperature is that will give us enough thrust to get off the runway, and it's 32 degrees. Or is it? So did you fall for the second most common classic blunder? Remember, the temperature we use or get from the rack manual chart has to be adjusted by 12 degrees in the real world to account for engine add ice on. So in this case, we need to take the 32 degrees from the rack manual performance line, subtract 12 and end up with a T-flex of 20 degrees. So let's fill in the RTOW limit box with the weight and the V1 so we can continue on. And just in case you're wondering,
you fell victim to one of the classic blunders. The most famous is never get involved in a land war in Asia.
okay, so step 9 calculates our TOW limit. That is, having identified a flex temperature that at least meets our performance requirement, what is the actual maximum takeoff weight we can lift today based on that flex? We do this by taking our RTOW limit and subtracting from it the adjustments we calculated in step 4. In this case, that was just for the low QNH. Continuing through the card, if there was some doubt about the intersection previously, perhaps we weren't using full length from choice, then we would finally populate the runway intersection now. In this case, we were always going to use as much runway as we could get our hands on, so it remains blank. So we now take our flex temperature, in this case the intermediate flex of 20 degrees, and write that in the T-flex box. Anytime you're at this point and you're about to write a T-flex in that box and you can see that the engine anti-ice is on, I suggest a quick double check just to make sure you're using the flex temperature after it's had its 12 degrees subtracted from the rack manual value. If you forget, you should pick this up when you set up the TMS, but we may as well get it right now rather than catch it later. Just saying. And as always, if we're within 200 kilos of our performance limit, we're required to do a standing takeoff. In this case, yep, we need to do a standing takeoff. So let's cross out the rolling. And finally, let's write the takeoff flap in the card, nice and big. Time to move on to step 10, the thrust settings. For that, we're back to the engine thrust table card. So step 10 is the thrust settings. We'll need our flex thrust N1, our reference thrust N1, and our climb thrust N1. We're back in the engine thrust table with the blue card for engine anti-ice on. So starting with N1 ref, we hit the ambient temperature of 8 degrees, work our way left pressure altitude, which in this case is closer to sea level than it is to 500 feet, and our N1 ref is 92.3%. And the climb thrust N1 is right here in the grey column beside T ambient on the engine thrust table, and it's 87 for engine anti-ice on. So finally, our flex thrust N1 also comes, unsurprisingly, from the engine thrust table. We're starting at the same ambient temperature of 8 degrees, heading across to the right to the flex temp we previously identified that met our performance need, in this case 20 degrees. From there we go down and we end up with an N1 of 88.9. Unsurprisingly, more than the minimum of 87 because we needed that extra thrust. So much for step 10. Let's move on to the V-speeds in step 11. For step 11, our V-speeds come mostly from the speed cards with a couple of caveats. First, we'll round up the takeoff weight to, well, actually, it's 36 tons. So let's grab the 36-ton card. Okay, so from the 36-ton card, flap 24 takeoff, the VR and basic V1 is 113 knots. Now we need to correct that VR for temperature and pressure. So our final VR will be equal to the speed card basic VR with a correction from the VR correction table. In this case, 8 degrees and sea level comes with a correction of -1 knot. So the VR for the toll card is 112 knots. Next, we occasionally need to consider a V2 correction, but since it's only required for takeoff weights of 28 tonnes or less in the turreted series, it's not applicable today, and the speed card V2 of 119 knots can go straight onto the toll card. And finally, the V1 must always be the lower of the RTOW limit V1, which we made a note of earlier, and the corrected speed card VR. In this case, the lower of the two speeds is 92 knots. Time to fill in the V1 on the toll card. And we're almost there. We can grab the VFTO of 172 from the speed card and write it on the toll card. As far as the toll codes goes, that's the end of the speeds. And just a final reminder that while we don't write the VAR speed on the toll card, we will be bugging it from the speed card where it's always VFTO plus 10 knots. Let's head towards the finish line. Step 12, noise abatement. While the source document for noise abatement is our JEP charts, Pioneer have published a quick reference noise abatement list at the beginning of the rack manual. This list conforms to any specific noise abatement departure procedure dictated by the airport authority, as well as Pioneer's SOP preference for NADP2 when noise abatement is required, but no specific procedure is specified. As always, indicate on the card the requirement. That's it for step 12. On to lucky 13. Our final step is to record onto the toll card the engine out procedure and the engine failure flap retraction altitude, or EFRA. Remember, of course, that if we have DP in the runway intersection name, then there's a special departure procedure to go looking for in the rack manual. But in this case, it's a straight out departure, which means straight ahead to 20 miles, establish a left-hand 5-mile holding pattern. And finally, our minimum engine failure flap retraction altitude is published in the RACM here as 1070. We'll round this up to 1100 for altimeter bugging purposes and write it on the card. With the card complete, it's time to hand it over to the other pilot for an independent cross-check. While this procedure is covered in the SOPM, the following points are worth noting. Cross-checking is a skill that, first of all, requires the knowledge and understanding of how the card was completed in the first place. You can't cross-check a card if you don't know how to prepare one yourself. Cross-checking requires you to consciously avoid or look for prejudiced information. This includes looking at the ATIS yourself, the load and trim sheet, the rack manual, the thrust card, and the speed cards. In all cases, finding the correct page yourself rather than accepting a previously selected page by the other pilot. With the toll card complete and cross-checked, before you hand the card back to the other pilot, independently set your speeds. When the card is returned to the other pilot, he or she should also set their speeds independently, and then the TMS setup N1 bugs and airspeed cross-check procedure can begin. That's the end of this example. I hope you managed to make it all the way through.